Hi, in this video we'll be doing a more challenging question on moment. The main difference between this new question and the previous question is that previously we had an assumption that the stick or the plank itself is massless and we didn't consider the weight of it. However, in reality, the weight of the plank should not be ignored. So let's see how this can affect our calculation when the weight is taken into account. So now please pause the video and try this question yourself.
A few moments later.
Alright, let's try to do part A. So it asks you to draw all the forces acting on the plank. So first of all, there must be a weight equal to 120 from the middle of the plank, and then the person will also add the weight, which is 480. At the same time, because think about this, the whole system is static, is in equilibrium, and therefore there must be an upward force supporting this system. That means the plank itself, and that will be the force from point A and point B, which are the support. So I will be drawing a force like this, and I call it normal force, or you can call it reaction force. And since we should not assume they are the same, and in fact they are not the same, as you can see they are not symmetrical. When the person is not at the middle, then obviously it's not symmetrical, and therefore they must be of different values. So let's name them N1 and N2. Part B, it asks you the total clockwise moment of the two weights about point A. So this is point A. I will advise you to cross it so that you know this is a point. Then the two weight, actually, like what I said, is going to give a clockwise moment, because if you try to think about point A is being pinned, and then that two weight is going to give this direction and also this direction, which is clockwise moment. And so for calculating that, we can say the moment going clockwise will equal to the force times the distance. And so I'll just write the number directly. So 480 times the distance, which is 1, plus 120 times the distance, which is 1 plus 1, okay, which is here, right, from this point to this point. So eventually you get the answer of 720, and the unit is Newton meter. Part C, it asks you to use the principle of moment. That means knowing that the whole system is in equilibrium, then the clockwise moment equal to the anti-clockwise moment, which is what we mentioned at the very beginning on the first page here. So this is so-called the principle of moment. Anti-clockwise equal to clockwise moment at any point if the system is in equilibrium. So for part C, then for the anti-clockwise moment, we will have the one from N2, so that is N2 simply times the distance, which is the whole thing. We all know is 4, but we should write 2 plus 1 plus 1. And then you may ask, hey, what about N1 then? Think about it. The answer is nothing, because, well, you can also do N1, but then what happened is, since it is force times distance, force is N1, but then the distance from the force N1 to the point that you are taking the moment, which is point A, is exactly the same point. This is a line, the force of the line passing through that point, and therefore the perpendicular distance is simply 0, and therefore if you want to calculate the moment, it's going to be the force times the distance, which is 0. So that means the effect is 0. So it is like when you have trying to turn something, say this pen, you have to add the force in this direction, right? So then it can turn. This is like the pivot. This is the point of turning. If you want to push it. But if you try to add the force here, there's no way you can turn it, because this is the pivot and you can't do anything with it, and therefore there's no moment. Part E is asking you the upward force from point A, which is N1 basically. And so the first thing that we need to recall is that the total net force is going to be 0, because again the whole system is in equilibrium, translational equilibrium. And so according to this, then we should know that M1 plus N2, which is the two upward force, the only two upward force, should equal to the total downward force, which is 600. And since from the previous question we already know N2 is 180, and therefore we can find M1 to be 420, and that is the force we have for point A. And that is logically sensible because that person is standing closer to point A, and therefore that normal force should be greater than the one that we have at point B. Part F. It said now the person will walk towards point A, which is the left side of the plank. And so it asks you what is the upward force from point B at the instant that the plank starts to tip. So think about this. If this person start walking towards this, sooner or later at a certain position, the whole plank would start to flip, right? Because it cannot balance on both sides. So obviously at the very instant that it start to tip means again it will start to rotate like that, it will flip like that, then the plank and the point B, which is here, will no longer be in touch. Okay, they don't have any contact, physical contact anymore. And in this case, you cannot have any normal force. It's literally zero. So that is to say, for part F, the answer would simply be 0 when it starts to tip. And part G, how far is the man from point A when the plank tips? So in this case, then we will need to define a variable because this will be the unknown. So from point A, right? So let's say it is distance D, and that will be the point where it starts to tip. So the most challenging part of this question is to think about how to set up this equation. You really need to visualize this properly in order to set up the equation, and that's very important skills in general in physics. So right here, allow me to erase all these things and redraw the whole picture. So if the man is now at point D away from point A, and so in this case that is the weight 480 Newton acting at this point, and then the weight of the plank is still the same 120 Newton, it shouldn't be changing. The force at point B will now be 0, so let's just skip it, don't draw anything. Here we can draw M1, a new M1, and this is basically how the picture look like. And so if you can accept this is what going to happen, then we can try to pick a point where we can try to take the total moment. So I would suggest taking the point A simply, so we don't have to worry about what M1 is, although it's very obvious that M1 is going to be 600 directly. And so in this case, what we can say about it is we would like to first say take moment. This is actually very important. Take moment at point A, because the question didn't specify that, and therefore you should specify always. By taking moment at A, then we should be able to find out the clockwise moment would equal to the anti-clockwise moment. And so the only two moments that you have actually is from 480 Newton and 120 Newton. And that is going to be 480 times D, because this is the distance D away from point A, and 120 is still the same. So 120 times 1 plus 1. So solving this equation can give you the answer of 0.5 meter, and that is to say the person can walk up to 0.5 meter. So if this is in scale, then I guess it's roughly around here only. We are not done yet. If you recall the principle of moment, the statement told us that you can actually choose any point for calculating the moment, and if this whole system is in equilibrium, that it doesn't really matter what point you take. As long as you take a particular point on the system, then the net moment should still be equal. So let's try to do a test and see whether or not you can still find the same number for distance D, which is supposed to be 0.5 according to our previous calculation. Let me choose a point for you. Let's try to choose the center of the plank. So the first sentence that you should write is to say take moment at the center of the plank. Okay, so I want you to perform the calculation, try it out, and pause the video now. Okay, so let me try to show you how we can do it. So here we should have the clockwise moment equal to anti-clockwise moment, and here again we only got two forces. One is 480, one is m1, and so for 480, the distance from 480 Newton to the point, which is center of the plank, is going to have a distance of d plus these 2 meters, so 1 plus 1 here. And for the m1, again, m1 is supposed, by the way, should equal to the total downward force, which should equal to 600. And so, well, let's write down 600 simply. Multiplied the 2 meter, so 1 plus 1 again, because this is distance from m1 to the center. And again, if you try to resolve this question, you have 480d plus 480 times 2 equals to 1000. Wow, it's getting way more complicated, but eventually the answer, yes, is still equal to 0.5. So I hope you can see and appreciate that physics, just like maths, there are different approaches to do it. As long as you uphold with the fundamental idea, fundamental law, you can still find the answer, the same answer, using different approaches.
Imagination.
And this is why we would trust and believe the statement of principle of moment, which is you can take it at any point. Okay, literally any point, even outside of the plank itself, actually it still work. Okay, you can try if you want to. So if you're okay with our previous example, I want you to try this past paper question. Pause the video and try it yourself first.
A few moments later.
Okay, first part, it asks you to calculate the moment of 3 Newton load about the pivot. So this is the 3 Newton load. And notice that the distance shown in cm is not really distance, right? It's actually the position. And so if you want to calculate, you have to show it's 90 minus 50. And so what I will be doing is I will say moment equals to force times distance. Once again, you should write the general equation first. And that would equal to 3 Newton times the distance, which is 90 minus 50. Or even better, you can write 0.9 minus 0.5, because you should write it in SI unit, which is in meter. And so eventually you simply have 3 times 0.4, which is 1.2. And in this case, then you can use the SI unit, which is Newton meter. Or if you use cm, you should convert it back to cm. Number 2, it asks you the 2 Newton dead load. So yeah, it's simply the same idea, force times distance. So I'll do it faster this time. Distance is going to be 20 and 50, so 0.5 minus 0.2, that means 0.3, and that means 0.6 Newton meter. And except for part 3, it is the force maintaining the meter ruler in equilibrium at the pivot, calculating the value of F. So here, we don't have to consider the weight because the pivot is at the middle. If we take the moment at the pivot, then the weight contributing the moment is going to be 0, just like what we mentioned earlier. So that is why we can ignore it. So F is actually like an external force. So what we could have here is we could say, since the whole thing is in equilibrium, then again, clockwise moment equal to anti-clockwise moment. This is a sentence that I would surely write. Then for the clockwise, that is going to be 3 Newton, that one, which we calculated to be 1.2. The other one, which is 2 Newton, that is going to anti-clockwise, plus the one that is for force F. Okay, and then therefore for calculating the moment of that, there will be F times the distance, which is 50 and 30, and that's 0.5 minus 0.3 bracket. And solving this, then we can have 0.2 F, and F is going to equal to 3. So 3 Newton is the final answer. Now part B, basically they change the whole setting, so it's not really relevant to part A. So here is that 1.2 is going to be the weight of the meter ruler itself, which is at the middle of the ruler, which makes sense, being the center of mass. And this will be an idea that we introduce later on, but yeah, just take it as the point where it will has the weight as a force. So it asks you to determine the position of 2 Newton load, so that the whole thing will again be balanced. And so obviously it's the same thing that you have the clockwise moment equal to anti-clockwise moment, and so the clockwise one will be 1.2 times the distance, which is 0.5 minus 0.3, with the other moment that will be 2 Newton times the distance d. Let's just take it as d first, and d is going to be the distance from 2 Newton to the pivot itself. And so in this case, you will be able to find an answer that is d equals to 0.12. And if you write 12 cm, then you are wrong.
NANI?
Read the question carefully. The answer that it asks you to write down is saying the 2 Newton load is at a certain cm mark. And think about this meter ruler. This is 50, this is 30, and that means this is 0, this is 100. If d is going to be 12 cm, then the position that you are having here is not really 12 cm. It's actually 30 minus 12, which give you 18 cm. This is actually at 18 cm, and this is 30 cm for the pivot. So the answer is actually 18. That is all for this video. In this video, you basically have tried to apply the idea of equilibrium, the two conditions. One is net force being 0 in all direction, and another one will simply be principle of moment. And more importantly, you find out that really it allows you to take the moment at any point. As long as the system is in equilibrium, the moment is going to be 0 in total. Lastly, depending on the question, we may also need to consider the weight of the plank or whatever that is supporting the object. Hope to see you again in the next video. Bye bye.